Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Muhammad Haikal from Unity Venture Capital Group in section 1 of Dr. Azwan bin Sapit class heat transfer. Okay, today I would like to, we as a group will present the topic of radiation in heat transfer. So before we start, I would like to explain about what are the fundamentals of thermal radiation. So let's proceed. So radiation, as you can see in the figure below, so that is a circular wall, and inside the wall is we have a hot object which obviously will be higher temperature than the wall. Okay, so around the hot object will be a vacuum chamber. As we know, if there is a vacuum space, it will be no molecule or particle in it. So this is the type of radiation. So in this situation, radiation occur instead of conduction and convection. Why? Okay, why the situation just mentioned before is not stated as conduction? Okay, now, okay, for conduction, we need a molecule that is mixed to each other around the hot object, so that the energy will be transferred by the molecule around it. Okay, so when the molecule collide to each other, then the energy is being transferred through it. Energy in the form, temperature in the form of energy. Okay, so when the condition is in vacuum, so there will be no molecule around the hot object, and then when there is no molecule, no value of thermal conductivity will be present. So as we know, every surrounding, or we have air or any gases or liquid, will having the value of thermal conductivity represented by letter K, small k. So when there is no molecule, we will know that there will be no thermal conductivity. So we can consider that the condition below is not conduction, because of there is no molecule and there is no value of K, and no conduction will be occur in this situation. Okay, next, why it is not called as convection? Okay, this is because for convection also there must be particle or molecule around the hot object or around the body. So in order to make convection occur, the particle around the body will transferring the heat from one particle to another particle. So let's say the hot object want to heat up the wall around it, so there must be a particle around the hot object to transfer the heat from the hot object into the circular wall. So when there is a no particle around the hot object, so there will be no route of heat of transfer from one point, that is the hot object, to another point, that is the wall of the vacuum chamber. Okay, so that's the reason why it is not called as conduction and convection, and we consider it as radiation. So as we know, when null set number equals to 1, okay, convection is related to null set number. So when null set number is equal to 1, the mode of convection is equal to the mode of conduction. Okay, when null set number is equal to 1, it is equal to H d over K, where H is the thermal coefficient, okay, come from conduction, and come from convection, sorry, and K, H d over K, K is the thermal conductivity. So when we don't have any thermal conductivity like the previous conduction, no molecules will brings to no value of thermal conductivity K. So when there's no thermal conductivity, so we cannot use null set as our equation, then convection will be considered as no present in this situation. So as I explained just now, these are the reason why conduction and convection are not considered as the process of heat transfer in this situation. Okay, so the similarity of these two heat transfer method, conduction and convection, is that both are requiring a medium to transfer heat from one point to another point. Okay, so for now we know that this condition shown is related to radiation. Okay, so we will explain further. Okay, first, there's several characteristics of radiation. Just I mentioned just now, for radiation, to the distinction between radiation and both conduction and convection is radiation didn't require any medium for the process of heat transfer. Okay, so one important application of radiation is that as we can see around us, we staying in Earth, and we receive temperature, high temperature from the sun. Okay, as we can see in the diagram, show that the average temperature of Earth is 20 degrees Celsius, while the temperature of the sun 5,505 degrees Celsius. Okay, but in between Earth and the sun, we have the medium, which is known as the outer space, at the temperature of negative 20 degrees Celsius. Okay, so in this case, we know that we can receive the heat of the sun from the Earth, and there is no medium between Earth and the sun. Okay, and we can see that the temperature of the medium is very low, and the process of transferring heat from the sun to the Earth did not change the temperature of the medium. Okay, because it is vacuum. So we can see in the graph, we know that the temperature of the sun is 5,505 degrees Celsius, while the Earth is at average of 20 degrees Celsius, while the medium for the energy to transfer from the sun to Earth is known as the outer space, is at the temperature of negative 20 degrees Celsius. Okay, so in this case, the process of radiation does not affect the medium temperature, which is not increasing the outer space temperature. It will remain at negative 20 degrees Celsius. That is the characteristic of radiation that we need to know. Okay, same as let me say a group of people that having a campfire. Okay, and temperature of the fire is 900 degrees Celsius, while the human body at the 37 degrees Celsius. So we can feel the warm temperature from the fire from a distance of, let's say, 1 meter, but the surrounding, the medium around fire is not changing directly 900 degrees Celsius. It will be a gradient change of temperature from the campfire onto the people around it. Okay, next, the characteristic of radiation that we need to know is fastest in the vacuum. What I mean by that is, in vacuum, radiation will occur on the speed of light. Okay, when vacuum, there is no molecule in the vacuum space, so that radiation will be occur at the speed of light, where CO, okay, we can consider as the radiation occur at the speed of 3 times 10 to the power of 8 meters per second. Okay, that is very fast. Okay, next, the characteristic of radiation is surprisingly can occur in gas, liquid, and also solids. Okay, now this is one of the important part, is the wavelength. Okay, the wavelength of radiation. Okay, as we know, Maxwell 1869 have mentioned about the accelerate charge and the changing electric current. Okay, both of these will produce a magnetic field against electric field graph, like shown in the diagram. What is the meaning? The meaning of wavelength here is the length from one field to another field. Okay, so that is the meaning of the wavelength here. Okay, so by that, wavelength is equal to c over frequency, where c is the speed of wave in the medium. We can calculate c by dividing the speed of light to the value of n. Okay, where n is equal to 1 for air and most gaseous type in the surrounding, 1.33 for water, and 1.5 for glass. So by calculating the value of c from speed of light and the value of n, we can insert the value of c into the value of wavelength, which is c over frequency. Next, lastly, the characteristic of radiation is Planck on 1900. Okay, so Planck has come up with an idea, which is energy actually being transported in particle. Okay, in particles. So by that, we can conclude from the previous characteristic of radiation that when energy that being transported by electromagnetic waves increase, the frequency will also increase, and the wavelength also will increase. So we can conclude that energy that being transported by electromagnetic wave is high when the frequency is high and the wavelength is low. We will try to solve a problem of radiation that is related to the engineering problem. Let's go to the next chapter. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and a very good evening. So my name is Muhammad Eri Zulkarnain bin Azahar and my metric number is DD180032. So today I'm going to present to you our project, which is, for my part, I'm going to discuss about our question 1. So basically, before we moving on to our part, which is the calculation, so we need to know a little bit about the fundamental or the information that we needed to use for the calculation that we're going to moving on in the next part. So first of all, for the question 1, so the question 1 is the radiation emission from a black ball. So the question said that it consider a 20 centimeter diameter spherical ball at 800 K, which is the temperature in Kelvin, and it is suspended in air as shown in figure below. So assuming the ball closely approximates a black body, so determine first, the question asks for us to find the total black body emissive power. And the second question, they ask us to find the total amount of radiation emitted by the ball in 5 minutes. And lastly, they ask us to find the spectral black body emissive power at a wavelength of 3 mm. So from this question, we know that the questions have given us the diameter of the spherical ball, which is 20 centimeter, and it also gave us temperature of the ball, which is 800 K, which is in Kelvin. And so for this question, we assume that the spherical ball behaves as black body. So to find the first question, which is the black body emissive power, so we could use the Stephan-Boltzmann law, which is EB equal to sigma T to the power of 4, and the unit will be in kilowatt per meter squared, whereas the sigma is in Stephan-Boltzmann constant, which is 5.67 times 10 to the power of -8, and the T is the temperature, which is in Kelvin. So if the temperature given in degrees Celsius, so we need to convert it from the from degrees Celsius to Kelvin. And then the second questions ask us to find the area, or ask us to find the Q radiation. So before we find the Q radiation, we need to find the area of spherical ball by using the formula, the basic formula of area for spherical, which is pi d squared. So which is d is the diameter of spherical ball. And then from the question, it also gives us time, which is in 5 minutes. So we need to convert it from minute to seconds, and then we substitute the information that we have into the formula, which is Q rad equal to EB times AS times delta T, and then the last unit will be in kilojoule, whereas EB is the emissive power, AS as the area of spherical ball, and delta T is the change in temperature. And lastly, the equation to find the spectral blackbody emissive power at a wavelength of 3 mm, we use this formula, which is Planck distribution law, and last unit will be in watt per meter squared. So that's all from me. Thank you.
Assalamualaikum. My name is Muhammad Azwan bin Fazil, and my metric number is DD180061. So I will be presenting the solution for the first question. So for question 1A, the question asks to find the total blackbody emissive power. So to determine the total blackbody emissive power, we must use the Stefan Boltzmann law. This one, EB is equal to sigma times T to the power of 4. So the constant will be 5.67 times 10 to the power of negative 8. And the temperature is 800 Kelvin. So this is the solution for question number 1A. So the ball will emit 23.2 kilojoule of energy in the form of electromagnetic radiation. For question 1B, the question asks us to find the amount of radiation emitted by the ball in 5 minutes. So firstly, we must find the area of surfaces, which is this one, pi d squared, and we will get around 0.1257 meters squared. And then we will convert the time from minute to second, which is 5 minutes to seconds will be 300 seconds. And to calculate the amount of radiation is by using this formula. We will get the answer 875 kilojoule, which that means the ball loses around 875 kilojoule of energy in the form of electromagnetic wave to its surrounding in 5 minutes. For the final question, which is 1C, the question asks us to find the spectral blackbody emissive power at a wavelength of 3 micrometer. So by using this formula, we will get the spectral blackbody emissive power is around 3846. I think that's all for question number 1, so we will move on to the question number 2.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azwan bin Sapit, and I will explain to you the fundamental and the formula that we will use to answer question 2, which is radiation incident on small surface. Okay, first of all, we will read the question. Okay, a small surface of area A1 is equal to 3 cm square, emits radiation as a black body at T1 is equal to 600 Kelvin. Part of the radiation emitted by A1 strikes under the small surface of area A2, which is equal to 5 cm square, oriented as shown above. Okay, so the question asks about 2 questions, which is first the solid angle subtended by A2 when viewed from A1, and then the rate at which radiation emitted by A1 strikes A2. Okay, so from the question above, also the picture, we managed to extract some information which is A2, A1, T1, theta 1, theta 2, and R. Theta is the angle, as you can see here, and R is the distance between two plates. Okay, so let's move on to question 1, question A. To find the solid angle subtended by A2 when viewed from A1, we could find by using solid angle formula. Okay, so the keyword here is solid angle subtended by A2. Okay, I've highlighted for you. And then we could determine by using solid angle formula, which is omega an over r squared. This is a solid angle formula. Okay, this is solid angle formula, which is A is area and r is the distance between the surface. Okay, so for the question above, the question asks about solid angle subtended by A2. Okay, focus on this A2. You will see here that the equation you will use A2 and cos theta 2 because the solid angle subtended by A2 when viewed from A1 can be determined to be this question since the normal of A2 makes 40 degree with the direction of viewing. So as you can see from this picture, A2 sees A1 by 40 degree angle. Okay, so that's why there will be cos theta here. So we will use A2 and theta 2 because the solid angle subtended by A2. Okay, so that's all. So next question B, we will find the red at which radiation emitted by A1 strikes A2. So the keyword here you want to see is radiation emitted by A1. Okay, it should be here. Okay, radiation emitted by A1. Okay, so first we need to determine the radiation intensity for black body. Okay, why we need to determine the radiation intensity for the black body? Because the formula of red of radiation emitted, this is the formula of radiation emitted. Um, it is equal to Q. Q is red of radiation emitted is equal to I. A1 cos theta 1 omega 2 to 1. Okay, so as you can see in this formula, we have I, we have A, we have theta, and we have omega. A1, we got the information. Theta also we got the information. Omega we calculate at the question A above. So here we have no I. What is I? I is the radiation intensity for black body. Okay, so the formula for radiation intensity for black body is I is equal to EB T1 over pi, which is also equal to sigma T1 power of 4 over pi. Okay, what is sigma T1? Sigma is actually a constant named Stephen Boltzmann constant. Okay, which is it is 5.67 multiplied by 10 power of negative 8. It is a constant, and T1 is the temperature of plate 1, which is 600 Kelvin in the question, and over pi. Okay, so then we will got I, we got the radiation intensity, and then we will use this formula to find the red at which radiation emitted by A1. Okay, so by reading again what the question asks, the radiation emitted by A1, you see here A1, we will use all the information of plate 1 only. See the radiation intensity for plate 1, area for plate 1, and theta for plate 1. Omega, we will use the 2 to 1 because that is what we calculated above. Okay, so after you insert all the information that we got, I is from here, A1 is 3 centimeter square, theta is I think 40 degree, and omega is from what we will calculated from A, then we will got Q. Okay, so that's all from me. So the question will be answered completely by my colleague, which is Hafiz Abba. Okay, so that's all from me. Thank you.
Assalamualaikum. My name is Muhammad Hafiz Albar, and let us continue to the solution for the question. So the main question is asked for the rate of radiation, and these can be calculated by using the formula below, which is Q dot 12 equal to I1 A1 omega 21. I1 is the intensity of radiation from surface 1 over here, and omega 21 is the solid angle by A2 when viewed from A1. So first we find the solid angle, which can be determined by using the formula below. Omega 21 equal to A2 over R squared. So since A2 is already been given over here, which is 5 centimeters squared, we just can substitute it into the equation below. However, we need to consider the angle between the viewing point of A1 and the normal from surface 2, which is equal to 40 degree. So the solid angle is equal to 5 cos 40 over r squared, which is the distance between A1 and A2, which is equal to 75 squared. Therefore, the solid angle subtended by A2 when viewed from A1 is equal to 6.809 times 10 to the power of minus 4 steradian. Next, we determine the value of intensity of radiation from A1 by using the formula E2 times T to the power of 4 divided by pi. So E2 is the Stefan Boltzmann's constant, which is equal to 5.67 times 10 to the power of minus 8. T is the temperature, which is already given, which is 600 Kelvin, power of 4 divided by pi. Therefore, the intensity of radiation is equal to 2339.043 watt per meter squared steradian. By acquiring two value above, we can find the rate of radiation from A1. Therefore, we substitute the value I1, which is equal to 2339.043, A, which is already been given 3 centimeters square, by substitute it to meter squared, we will get 0.0003 cos 55 times the solid angle, which is 6.809 times 10 to the power of minus 4. Therefore, we will get the rate of radiation emitted from surface 1 to surface 2 is 2.741 times 10 to the minus of 4 watt. So that's all for question 2 and from us. Thank you.